We don't take any of the integrals. Each diagram is represented as a point with all the parameters specified. We just sample this and sample. And that's why if you ask me, okay, have I ever written diagrams of 44? No, I don't even know them. And I don't have to. I simply have to make sure that my random walk is ergodic, and I'm not going to miss anything by design. So I have a chance to sample everything.
It seems like the diagram order is like somehow a very different way to do the walk than, say, like changing some momentum or something.
I would say, well, it's a discrete variable. This is a continuous variable. So it's probably even easier.
Okay.
You change discrete variables by plus minus 1. That's what we typically do. And ultimately diffuse to higher order and then come back. Same with topology. We simply commute lines in different ways and see, okay, if the diagram is reducible or not. That's the only filter. And here we just play random numbers to suggest some internal variables. Fundamentally, more or less the same. So let me now just say, okay, that's the design, how everything is supposed to work. You take quantum magnet, you fermionize spins, you formulate the Hamiltonian, which is perfect in the sense that whatever answer I get from those diagrams for fermions is faithful solution for spins, as long as it works and converges. So let me now show some results for the triangular lattice Heisenberg interferomagnet, because the first sentence I read in most papers, oh, it's a frustrated system with the same problem, so Monte Carlo doesn't work. Well, there is Monte Carlo and Monte Carlo. The Monte Carlo in the prime representation, which works with spin, fails because of the same problem. But Feynman diagrams don't have particles. They're mathematical objects. So in the space of Feynman diagrams, it's also Monte Carlo, but it will work. Well, second, Feynman diagrams are in a thermodynamic ensemble. I have infinite system. So because when you draw a Feynman graph, you sample all internal variables. There is no limit on the system size. Formally, it's the solution of the thermodynamic system. Infinite number of spins. And that's what everybody does at the midfield level. You just draw first order diagram, and you claim the answer. But the answer is for the whole system. There is no discussion of finite size effects at the midfield level. That's exactly the same here. When you compute diagrams, it's a thermodynamic answer. That's why it's not about spins. But it's a lot about sign, because it's a true statement that the number of diagrams will increase factorially. And then you say, oh, if you don't have small parameters, and the number of diagrams is increasing as a factorial, then probably there is no convergence in the first place, because the factorial will beat any small number in front. So, strictly speaking, if diagrams don't cancel each other to a very high degree, there is no hope for convergence. And that's the first thing which you check. You go to high order diagrams and you check that high order diagrams don't change your answer. And you can check it at one temperature, another temperature, and just see that it works. So we go, well, this is relatively high temperature, and this is already T of order J. In this case, T equals J. And I still see essentially perfect exponential convergence pretty fast. So at order 4, I'm already more or less finished with 3 digits. But the number of diagrams which I have to collect here is substantial. So essentially at the 7th order, it gives me the arrow bar, roughly the sense how accurate the answer is. But it's okay on the scale of 100,000 diagrams, but they contribute nothing compared to the 6th order. Each diagram is of order 1 or bigger. If you take individual diagram, it makes a huge contribution of order 1. On this scale, this would be, I know, up, back and forth. And all 100,000 of them contribute nothing. They just define my arrow bar, how confident I am that I am finished. And that's roughly to see the comparison, what we have in terms of diagrams which are self-consistently defined versus high-temperature series expansions. So the best we can find in the literature is by Marcus Riegel and Rajiv Singh. And essentially, well, J equal 2, T over J equals 2, it's here. The high-temperature series expansion converge here perfectly well. Well, we also converge. Now at T over J equal 1, the high-temperature series expansions explode. You have to manipulate the data using, say, PD approximants to continue, but we still converge exponentially, and we see the same at any temperature which goes down. So it does work, but at some point we start failing. So essentially, if you take high-temperature series expansion, extrapolate using PD for the uniform susceptibility, there is a special property of uniform susceptibility. In high-temperature series expansions, it's easy to calculate properties which are equal time correlation functions, because you have operator, another operator, and you do expansion. it's very hard to do properties which I would call static response, because for static response you have to do those two operators at different times, imaginary times, and integrate. But then it's much more difficult calculation. Why do you don't care about this for uniform susceptibility? Because magnetization commutes with the Hamiltonian and there is no time dependence. So uniform susceptibility is easy to compute. But getting the full magnetic response everywhere in the Brillouin zone, the static response function would not be possible even with high temperature series expansion. So for uniform susceptibility, just because Padé approximation can be done and the quantity is good, we can simply calibrate that we're doing everything right. But every other answer in the Brillouin zone for static response function cannot be already computed using high temperature series expansions. But we see that, okay, well, we can go to substantially lower temperature. Here we fail, slightly below we fail, not for reasons of convergence. The system starts to order. So you see that, well, my response function is getting a peak which is getting sharper and sharper. Almost everywhere in the Brillouin zone, the function more or less saturates to some value. But at the k vector, it keeps increasing in size and getting higher and higher and higher. So, okay, between here and here, it's already an order of magnitude or more. The correlation length starts getting big. But what does it mean for diagrams? It means that in the response function, I'm getting close to 0 in denominator. But all diagrams are kind of using this function. So essentially, effective interactions start getting large. And it's very hard to control the code. Because it's saying, well, the system starts to order. And this is very difficult for diagrams. So if you want to say, okay, Feynman diagrams can handle long-range order easily, no. Because it's all about getting very close to 0 in denominator, and any statistical noise can just kind of break the nice properties of your code. So essentially, yes, we can work till the point when the system starts showing order. And then it's very hard.
So far you agree with the Padé, or you can do better than the Padé?
No, it's roughly the same level. The Padé starts to split here, and we have some error bar for uniform susceptibility. For any other wave vector or for static response, there is nothing we can do with high temperature. There is no answer. We still have the answer for the entire magnetic response because it's part of the code.
So the Padé is coming from the high temperature expansion?
Padé is coming by doing Padé approximation of how, well, Padé is essentially doing the following. You have some high temperature expansion, but it's almost analytic. So you have coefficients, but you know the analytic structure. It comes with temperature to certain power. And then you say, what if I write down the ratio of two polynomials to high and high order, so that the Taylor series expansion of this ratio is the same. But then this function can be taken much further in temperature. So the series as they are will stop here. That's where you start losing the Bayer series. Well, but you can do the resummation. I'm not saying it's bad. If it's doable, it's a good technique to do Padé approximations.
Is it the same power in the numerator and the denominator?
No, you can play this game. Can be 5, 5, can be 6, 7, can be 4, 8.
Is it sensitive?
No. If you want to claim a good answer, essentially, well, when I say Padé 1, Padé 2, there are two curves. That's more or less the spread, how you play the game between different powers. So it has to be insensitive, but otherwise you have to claim it as an error bar.
But sorry, I mean, it turns around. That seems to be a qualitative thing.
The system is ordering, and that's why the...
Okay.
Well, you see, if the system wants to become antiferromagnet, you apply a homogeneous field. It doesn't want to do anything because they are opposite, and the homogeneous field is barely polarizing the system. So it's simply the reflection that spins want to order antiferromagnetically, and they don't want to react to the external field. So they go through the
power is method on the other side is very impressive.
On the right.
Okay, so at the level of predicting properties of frustrated magnets between J and some ordering temperature, probably we are completing the job. So we can describe this region faithfully. At least, okay, for the future experiments, if they cool the system by a factor of 5, we will be ready. In 3D, if there is a transition, because in 2D the problem is the system orders, but there is no TC. And the correlation lengths will keep diverging like crazy exponentially without any TC. In 3D, large correlation lengths means you are very close just a little bit and you have a phase transition. Just like in resonant fermions, we can measure TC by seeing how the pair correlation function just blows. In 3D, probably we'll be able to say what is the transition temperature. But in 2D, it's a special case. But now I would like to discuss one fact which still confuses us. So it starts like this, it's his history. So you can compute, just because we have the entire correlation function at all distances, you just compute the spin-spin correlation function, it's chi, as a function of distance. So it's SZ correlation function as a function of distance. And we see that, well, okay, some places like 0.3, this is distance from the origin, but that's roughly, you can count how many points. 1, 2, 3, okay, that's 0.3 and 0.7, they're shown in black. They have enormously small correlations with the origin.
What are those dots? They got different colors?
Well, do you see, well, the triangular lattice antiferromagnet is believed to be the 3 sublattice magnet. I'll explain.
Color.
No, it means this one and this one and this one and this one, 0, 2, 5, 10, 6, they form A sublattice. The blue ones are forming B sublattice, and those are forming C sublattice. 120-degree structure. Okay? So it's just color coding A, B, C for the triangular lattice, because the belief is that, well, it's triangular, it's a structure at 120 degrees with 3 atoms in the unit cell. So it's 1, 2, 3, 3 atoms in the unit cell. Strictly speaking, 0 and 3 have to be correlated antiferromagnetically, and they are antiferromagnetically correlated here at low temperature, but enormously weak. Why it's enormously weak? Because if I slightly increase temperature to 0.5, they actually become ferromagnetically correlated. So we decide, oh, cool effect. Well, previously people didn't know it because it happens at sufficiently large distance, and it was impossible to calculate this property at large distance. We decide, okay, it's a cool kind of reversal of correlations with temperature. Only at very low temperature they are correlated in the proper fashion, as the ground state predicts, but at high temperature they are correlated in the wrong way. And then the desire was to call it a quantum effect. But just in case, we decided to simulate the classical Heisenberg model when you replace spin 1/2 with unit vector and simulate the same Heisenberg model classically, and we have seen the same. There is a reversal of correlations for sites 3 and 7 even in the classical Heisenberg model. So that's the end of the quantum effect. But then we found something very strange which we still don't understand. If you normalize the response function to unity at the origin and you plot the quantum answer, it's kind of a fingerprint because it's a logarithmic scale. Correlations jumps up and down and sometimes change sign. But if you do quantum static response function as a function of space, there is a classical response function at slightly at a different temperature, but they're exactly the same. With our accuracy of 1%, they were exactly the same. And you go to another temperature, same story. You go to high temperatures, exact match. Low temperature, exact match. Formally, this is not supposed to happen, because quantum spin 1/2 is not the same system as a classical unit vector. But what we see is that the shape of the static response, the entire fingerprint, is exactly the same. With this accuracy of 1%, it was exactly the same. Call it 2 or 3 digits the same between quantum and classical. We have no clue why this is happening in a 2-dimensional triangular lattice antiferromagnet, but that's an observation. So you have quantum to classical correspondence. For any quantum temperature, I can name a classical one when the two functions will look the same, with accuracy of 2 or 3 digits.
So only in frustrated lattices, if this lattice is not frustrated, you don't have
This is
to find-
triangular lattice.
Oh.
Yeah, I'll come to this.
Okay.
Yeah, we kept asking questions. Because formally we understood, okay, this cannot be an exact statement because it's kind of outrageous that spin 1/2 will behave the same way as classical. But it does. At any distance, at any temperature, it does behave the same here with 1% accuracy. So let me finish kind of this story. We still don't understand why this is happening. But then you start extrapolating the data. You say, okay, let's see the relation between quantum and classical temperatures on one plot. It's kind of looking boring. We understand the limiting case, but it looks boring. And if I simply extrapolate in the most naive fashion, I end up here. It looks an innocent plot, but it implies that ground state in the quantum model, T0, looks the same in terms of static response as a finite temperature state of the classical model. So you immediately read it has to be a spin liquid then, because at finite temperature, classical spins cannot be ordered. So it has to be a spin liquid. Of course, well, this is subject to the statement that, okay, the naive extrapolation is probably too naive, you need more points, and maybe it will turn around and ultimately go to 0. So ground state in classical looks the same as ground state in quantum. Still possible. So at this point, I would say it's 50-50. We are shooting from a large distance. Why we kind of think there is still some intrigue? Because 0.28 is not a random number for the classical system. We just extrapolate naively, but we ended up with this number. But what's known about this number from classical simulations It's more or less already, well, Kawamura was predicting this for ages, counts 30 years. And more recently, there were several simulations. For example, you take classical Heisenberg model in finite magnetic field. It's a phase diagram which has different phases. I know, fully polarized because it's a strong field or paramagnet here. Then you have another phase, 120 degrees. But look at the phase transition lines. They all converge. Data-wise, you would say, well, you have to hit the horizontal axis. Simply the authors don't believe it exists and they draw the dashed line. But this dashed line is simply not believing that the phase diagram is hitting the horizontal axis. But Kawamura was claiming that there is a phase transition in the classical model at zero field for 30 years, and he has different data to analyze, maybe noisy, but okay. He is following a peak in the so-called vorticity modulus and extrapolates everything and gets 0.28. So for him, 0.28 is a special number, which is the chirality transition in the chiral order in the classical system. Whatever we mean in the classical system, 0.28 is a special point. Whether it's a very sharp crossover, as indicated here, maybe very sharp crossover, or the actual chiral transition. And that's why we think that maybe there is a chance that it has some significance. But either way, suppose we are not right with this one, but the correspondence holds, I will discuss it. But you ask the question, okay, obviously we decide, okay, if there is a correspondence on a triangular lattice, why not trying square lattice? Because square lattice you can do by path integral Monte Carlo simulations to any degree of accuracy. 4 digits, 5 digits, you name it. And classical simulations also can be done to very high accuracy. And the answer is yes. On the square lattice you have same correspondence at any temperature and any distance, but it's not exact. Since we can measure 4 digits, we see that the correspondence fails at the level of 0.3%. At this level, we already see it's a different response function. But it's different only by 3 parts in 1,000, relative accuracy. But it holds at any temperature and any distance. Well, and you also see that on a square lattice, the correspondence does bend down and ultimately arrives to 0. So maybe the same happens on a triangular lattice. We just don't know yet. So for us, it's still puzzle why this accuracy, because spin 1/2 is not a unit vector. For this, we don't have good explanation, and we don't know yet how general this phenomenon is. But if it's true in two-dimensional systems, then some kind of predictions can be made very easily. Again, this slide is partially speculation, because I'm saying if QCC holds, what kind of predictions you can immediately make from this statement. If the correspondence curve doesn't go to 0, it's a spin liquid because it's classical system at finite temperature. Well, can be different. Suppose that the classical ground state is disordered. And we know that if I take Kagome antiferromagnet, classically it's a disordered ground state with finite entropy per particle. And then nothing helps me. If you have the correspondence and the quantum system arrives to 0, 0 classical corresponds to 0 quantum, and you have correspondence, massive degeneracy in the classical state implies massive degeneracy in the quantum state, and we have a spin liquid. So if there is a correspondence, and we are eager to measure whether it's there or not, for the Kagome antiferromagnet, I don't have to suffer much to predict the spin liquid. Because if the correspondence is there, there is no escape. The quantum ground state will be disordered. Well, finally, the easiest case would be you have the correspondence and there is a phase transition in the classical model. Just draw the horizontal line. Just imagine this curve has a different behavior, but the horizontal line can be drawn and I say, okay, this quantum temperature will correspond to this classical temperature which has a phase transition. There has to be a phase transition in the quantum model. Okay, those are the implications of this correspondence which we do not fully understand yet. Okay, so that's with regards to the answers. And let me just briefly mention, if I have 1 minute, that the whole technique of fermionizing spins can be generalized to arbitrary spin or arbitrary lattice boson model. And essentially it goes as follows. Any spin projection or any bosonic occupation number, you can map it to one fermion which is occupying a particular state. Okay? So every single state of the spin projection or bosonic occupation number, you map it to with one fermion. Well, if you have spin 5, I will need 11 fermions to represent it. Okay, I have 11 fermions to represent it. Then I simply write down my Hamiltonian as some matrix elements which change the colors of those fermions. I change the species of the fermion on a given site without changing their occupation numbers. So those are the matrix elements, and those are projection operators. Here you change the colors of your fermions, the species, and I project everything else. I say, okay, this Hamiltonian can act only if the rest is empty. Well, but this is a polynomial in fermionic degrees of freedom. Any projector is a polynomial, so the product of two projectors is also a polynomial. And then I say this Hamiltonian will be dynamically perfect. It will not couple to a physical site. And I just go through the same exercise that if I have a chemical potential and I look at the partition function of the unphysical site, which is completely decoupled from the rest by projectors, well, you simply sum the degeneracy of all possibilities, how you can create n fermions. That's the contribution. Well, okay, I simply have to satisfy that this is 0, and by same theorem, which was mentioned already today, fundamental theory of algebra says there is always a solution in complex numbers. So I'll always give you a complex chemical potential which will perform the projection. So I'll have my fermionic Hamiltonian, and chemical potential will do the job.
Wow, that's very nice.
Okay, so what's the price to pay? Right now we're at the level of two-body interactions. But if I go through this exercise of higher spins, I'll have maybe 10 body interactions, 12, maybe higher. I don't know how well this will work, but the pictures are nice. Strictly speaking, you have your diagrammatic technique for any spin, Fermi or Bose system. And also, yeah, but how far we can go with this, I don't know. Nobody has programmed any of this, so we're still at this level. But you see that, okay, it's still promising to go this way. Yeah, I'll stop.
Questions?
Has anyone looked for or seen the quantum classical correspondence in one dimension?
Oh, yeah, sorry, I forgot to mention. Probably it was on the slide.
Oh, sorry.
I just didn't say it. No, I didn't say it. I was supposed to put it here. Yes. It's not a fine print. It says in 1D, it miserably fails.
Are there other questions? Martin.
So do you have any picture how the state might look like if it really converges to point 2A? Is it kind of a superposition of like this guy?
No, in terms of correlation function, it looks like a power law with power 1/4. But if it's the phase transition point in the classical system, it's kind of critical spin liquid.
So the classical system is right between, I think you showed the diagram, either these guys at like 60
No, that's what
degrees,
people think
and
about
then-
the ground state. And that's the ground state of the classical system. The ground state of the classical system, if I go vertical here, it's 120 degrees. But quantum doesn't want to go here yet. So quantum goes to a finite classical temperature, which means quantum will never know about your 120 degrees. It will be stuck at the Cairelli transition.
Thanks.
Are there any other questions? All right, let's thank our speaker again.